Welcome back, everybody. In this video, I'm going to be going over an unusually nerdy dive into the definition of circularity and cylindricity. So what got me going down this exploration of circularity and cylindricity is that I saw an example online and someone said that for a pin with a sufficiently large size tolerance, if you applied a circularity, a very small circularity tolerance, you could still end up with a situation like this where you've got discs that are sort of stacked on top of each other and offset, and this might pass inspection because as long as the actual mating envelope, the unrelated actual mating envelope, I should say, is within the size tolerances and each local measurement is within the size tolerances, this could have a circularity measurement of 0. And I'd like to show you why that's incorrect and then go and push a little bit further and look at what the actual definition of circularity is and how it relates to cylindricity. So the definition of circularity is essentially if you are to take an axis or some sort of spine, if it's a curved feature, and take a cross section perpendicular to that axis, all the points of the feature that you see should be equidistant from that spine or axis. And a circularity tolerance zone specifies a zone bounded by two concentric circles within each circular element of a surface shall lie. And this applies independently. And I think that statement that this applies independently is where the person got the idea that if those discs were offset, you could still pass a circularity tolerance zone because, well, each inspection is independent. But let's look at this note at the bottom here. It says C ASME Y14.51M, which is the mathematical definition of the Y14.5 standard, for further information. So this is the 1994, I believe 1994 edition of the mathematical standard. And this highlighted part, it adds an important note to the definition. The concentric circles defining the circularity zone are centered on the axis. So it's not just that you can have a pair of concentric circles anywhere. Those concentric circles are centered on the axis that you are inspecting along. Now, the astute of you might be asking, well, what's this axis or spine that they're talking about? How do we define this axis or spine? And that's a great question that they said explicitly in the 2018 standard. There was no explicit information on this as far as I could tell in the earlier standards. But in the 2018 standard on this image here, they added the note, each circular element of the surface in plane perpendicular to the axis of the unrelated actual mating envelope. So the axis, or spine for a curved circular feature, would be the unrelated actual mating envelope. And this is interesting. This got me wondering, how does this relate to the cylindricity? Because I couldn't find that note anywhere in cylindricity. And let's look at the cylindricity definition. So cylindricity is a condition where you have all the points equidistant from a common axis. But a common axis does not necessarily mean the unrelated actual mating envelope. So why does this matter? Well, on this note below here, it says that cylindricity is a composite control of form that includes circularity. So cylindricity is supposed to control circularity. So that got me thinking, if you were able to have an axis that was not the same as the unrelated actual mating envelope axis, could you have a condition where circularity and cylindricity are not controlled in the same way? And the answer is yes. So if you were to have an edge error that is, any size really, and an otherwise perfect feature. In this case, I've made it very large for demonstration purposes, but in this case, you would measure a circularity of 5 millimeters. And if you were to take the cylindricity measured around the unrelated actual mating envelope axis, it too would measure 5 millimeters. However, because it does not say specifically that the axis that these concentric cylinders are centered on is the unrelated actual mating envelope, maybe there is a more optimal orientation for these cylinders. And that more optimal orientation is at an angle so that the inner cylinder touches the bottom of the edge error at one end and the outside of the cylinder at the other end. And if you were to do this, you would measure a cylindricity of 4.999 millimeters, which is less than the circularity measurement. And you may be saying, well, why does this matter? And functionally, it does not. It does not matter functionally. Basically, you would, with any reasonable edge error, you would treat this as the same. However, it is interesting that there is this little artifact in the standard that either this means that the cylindricity by definition must be around the unrelated mating envelope axis, or that this was a mistake or oversight and should be corrected. I think in either case, in the next version of the standard, it should be said explicitly that cylindricity is to be measured around the unrelated actual mating envelope axis. So hopefully you enjoyed this deep dive into a very nerdy and specific part of the Y14.5 standard. And hopefully you have a better understanding of what cylindricity and circularity actually mean now.